Hello again, my dear students, and welcome to part number 2 with our semiconductor P-N junction lecture. If you remember, in part number 1, we have discussed together what we call the IV characteristic curve for a dot. We have found that this IV characteristic curve can be classified or can be divided into 5 portions. First, what we call the thermodynamic equilibrium point. This is the origin point when the voltage applied is equal to 0, and accordingly the current is equal to 0. Then, whenever you increase the forward voltage, but still below the building voltage V naught, you will have a very few current flowing in the junction. Once the forward voltage is greater than V naught, the current will increase exponentially with the voltage. On the other hand, when you insert a reverse bias to the junction, you will have a very limited current due to the minority carrier. Till you reach what's called the breakdown voltage, then the current starts to increase significantly, and you will have a breakdown to your device. This is generally how the IV characteristic curve looks like. Now, our target, or maybe our challenge in this part, is to transfer this IV curve into a circuit element modeling, to insert this diode into a circuit and to start analyze the circuit containing this dot. So what we are going to do is that we are going to make some sort of a simplification to this IV curve so that we can insert it in our circuit model. Herein we will have different models depending on the level of simplification that we are going to implement. So we first have this IV curve, as you can see. The first step is to make this IV curve as simple as possible. Accordingly, let's think first about the IV curve, the concepts of the IV curve, how the IV curves looks like, or how we can extract information from IV curve. Accordingly, let me first start with this white paper. The most easy IV curve ever you have seen is the Ohm's law IV curve for resistance. So we know that V equals I times R. Accordingly, this is the voltage, this is the current, and here is the relation as mentioned by Ohm. If you calculate the relation here, or the slope of this IV curve, you will find that it is equals to I over V, which is 1 over R. So the slope here equals to 1 over R. Accordingly, by varying the R, the slope will vary. Let's start together to plot two extreme conditions. What if R is equals to 0, and what if R is equals to infinity? Please remember that R equals to 0 represents that short circuit condition, and R equals to infinity represents the open circuit condition. But the question is how we can reflect this on the IV curve. Let's see. Okay, so whenever R equals to infinity, and knowing that the slope is 1 over R, that means that the slope will be equals to 0. So how we can plot a slope equals to 0? A slope equals to 0, that means that there is no variation in the y-axis. So whenever you have a horizontal line like this slope is equals to 0, because delta y is equal to 0. So whenever you have a horizontal line like this, that indicates a 0 slope, which indicates an infinite resistance. On the other hand, when your slope is zero, when your resistance is zero, that means that your slope is infinity. So how we can plot a slope equals to infinity? That means that the variation in x is equal to zero, which will lead to a vertical line. A vertical line means that the variation in delta x is equal to zero, and that's why the slope is equal to infinity. So whenever you see an IV curve like this, that means that you have a zero resistance. And whenever you see an IV curve like this, that means that you have an infinite resistance. Okay, the question is, what is the correlation between what I mentioned and the characteristics for a diode? Okay, let's see. Okay, perfect. So typically the IV characteristics for a diode looks like that. This is the IV characteristics for a diode. We have here, this is a VN node, and this is a reverse, and this is a. What we are going to do, my dear students, is that we will make some sort of simplification to this resistance, to this IV curve. We are going first to ignore this V node. And we are going to say that this is not an exponential. Let's say that this looks like this. It's a totally vertical line. And that this is a absolute zero. So let me return back to my slides for a while. So what we're going to do, my dear students, is that we're going to say that this IV curve can be summarized to this format. Again, this is a simplified IV curve. This is not a realistic one. We will call it an ideal diode. So based on our understanding to the IV curves, whenever you have a vertical line, that means that the slope of this line is equal to infinity, which means a zero resistance, which is this case. And whenever you have a reverse line, that means, whenever you have a horizontal line, that means that you have an a zero slope, which is an infinite resistance. So simply, whenever you are dealing with an ideal diode, what you are going to say is that you have two conditions, a reverse condition or a forward condition. In the reverse condition, the diode will be treated as an open circuit. In a forward condition, the diode will be treated as a short circuit. And that's all. It's a very direct and very simple way of modeling an electrical diode. So the question is, how we can classify or how we can distinguish our diode? Is it a forward or reverse? The answer is related to the biasing. If the P type, which we will call it the anode, which is this base of the triangle, is connected to the positive, and the cathode, which is a negative terminal, is connected to the negative, I mean, you are connecting what we called previously a forward voltage, then it's short circuit. If the potential is reversed, I mean the higher potential is connected to the cathode and the lower potential is connected to the anode, then it's reverse. So it's very simple to distinguish if your diode is a positive connected or a forward bias connected or a reverse bias connected. Now let's start with an example. And let's start with a DC example. A very easy one. Let me now return back to my slides, just the camera, and start solving this example. Okay, perfect. So the first example is as follows. We have a battery, which is a 10-volt DC battery, connected to 1 kilo ohm resistance and then you have a dot. And this diode is connected to the ground. I told you, please calculate the current flowing in this resistance. So what you're going to do as follows. This is a high potential node, and this is a low potential node. That means that the current is flowing in this direction. This is I. As far as the current is flowing in this direction, that means that the voltage here is greater than the voltage here. The voltage on the anode is greater than the voltage in the cathode because the current flowing is from higher potential to the lower potential. Accordingly, your diode is in the forward bias. Whenever your diode is in the forward bias condition, that means that you can replace this diode by a short circuit. And then you have this 1 kilo ohm resistance, and this is a short circuit. Now, it's maybe a high school problem. Whenever you have a voltage and the current, so the current is voltage and resistance, so the current is voltage over resistance. So it's 10 volt over 1 kilo ohm, the output would be 10 milliampere, the current flowing in this transistor, sorry, in this resistance. So it's very easy. Just we check the direction of the current based on the voltage, then we decide that this is a forward bias, we replace this diode with a short circuit, and that's all. Okay, let's have another example. Now, let's assume that we have a thermal circuit. Again, this is 10 volt. This is 1 kilo ohm. But now your diode is reversed. So the current flowing here, called I, this I makes that this voltage now, the cathode voltage, is greater than the anode voltage. The current is flowing in, down, this is a reverse bias, not a forward bias diode. Accordingly, you will say that, okay, this is a reverse bias diode. Then what you are going to do is to replace this diode by an open circuit. And this is 1 kilo ohm. Now, as far as you have an open circuit in your circuit, that means that the current flowing in the circuit is typically equal to 0. No current flows in an open circuit. But I may ask you somehow a difficult question. And I told you, please, calculate what we call VD, or the voltage drop here. The voltage drop on the open circuit. It's very easy, my dear students. This is grounded 100%. And the current flowing here is 0, which means that this is a short circuit. The resistance doesn't exist because the current is 0. Accordingly, if this is a short circuit, this is 10 voltage. So this is 10 and this is 0. So the VD, or the voltage drop on the diode, is 10 voltage. No voltage drop in the resistance because the current is 0. And all the voltage drop comes to the open circuit, which is a diode. This is one of the tricky questions. Okay, perfect. Let's go to the next question. Okay. Let's say that we have a circuit like this. No, I'm sorry. Okay, let's say that we have a circuit like this. This is R. This is some volt, let's call it Vs, a sinusoidal AC input, and this is our diode. And I told you that this have a sinusoidal signal like this. So this is Vs, and this is negative Vs. And you have a diode and resistance. And I told you, please plot the voltage output from these resistors. Perfect. So what you are going to do is as follows. You have to decide either your diode is a forward bias or a reverse bias. Accordingly, if it's a forward bias diode, you will replace it by short circuit. If it's a reverse bias diode, you will replace it by short circuit. So first, in order to decide if it's a forward bias diode or a reverse bias diode, you have to know the polarity of the voltage or the polarity of the current. Let's start with the positive voltage. If the voltage here is positive, I mean the positive cycle. In the positive cycle, that means that the current flowing is in this direction. This is a positive terminal, and the current flowing here is this. Assume that if you have a DC voltage here, so the current flowing from high potential to the low potential and rotates. Accordingly, in the positive half cycle of this sinusoidal signal, the polarity or the direction of the current will agree with the direction of the diode. I mean, the anode voltage is higher than the cathode because current flowing in this direction. Accordingly, in this half, the circuit will be, or the diode will be a short circuit. However, whenever you have a negative voltage, which is the negative half cycle of the circuit, this polarity will reverse, and then current should flow in this direction. Because now this voltage is negative, so higher, this is grounded, so it will flow in this direction. So in this case, your diode will be treated as an open circuit. Accordingly, you can say that this is your original circuit. We have here a diode and a resistance. And this circuit will be divided into two cases. When Vs is greater than 0, I mean it's a positive, then you will replace this diode by short circuit. When Vs is smaller than 0, I mean it's negative, then you will replace this by an open circuit. So this is the version where the voltage is greater than 0, and this is the version where the voltage is smaller than 0. Of course, when the voltage is greater than 0, then this is a short circuit, and that means that the output will typically equal the input. As you can see here, this is a short circuit, this is a short circuit, so the output and the input are parallel, and voltage in parallel are equal. However, when the voltage is smaller than 0, we have this open circuit, which means that there is no current reaching to this resistance. And that means that this is a short circuit to the output, and the output will be equal to 0. So this circuit will pass current only if the voltage is, or will pass voltage actually, only if the voltage is greater than 0. Whenever the voltage is smaller than 0, no voltage will be out, or the output voltage will be equal to 0. So let's return back to this circuit here. As you can see, my dear students, we have two versions of the circuit. This applied whenever the voltage to the source is greater than 0. However, whenever the voltage to the source is smaller than 0, we have this open circuit. Accordingly, we will have this shape. This we will call it later on. We will discuss this in the next part, what we call the half-wave rectifier. Whenever you pass only the positive portion of the sinusoidal and you get rid of the negative portion of the sinusoidal. So we call this as a half-wave rectifier. So this is one of the most important applications for our diodes. Now let's go to And next, now we have two examples for our ideal die. We started with this ideal die, and we have two examples, one with a DC circuit and another with an AC circuit. In both examples, we have treated the die as what we said, or what we term by an ideal die. But please don't forget that the real IV characteristic of a die is not that easy. It's a real characteristics. So before proceeding to the real characteristics, let's make another example, which is this problem. Let's try to solve this problem together before going to the next step with the electrical diode. Okay, what is this problem? In this problem, we have a voltage source, which is a sinusoidal voltage source, Vs, with a 24 voltage peak amplitude. Find the fraction of each cycle during which the diode conducts. Which cycle of this voltage will conduct? Here we have a diode, a source, which is 24 voltage. We have a 100 ohm resistance. We have the diode, and we have a 12 volt DC voltage. So we have a DC source and an AC source. Let's go together and start solving this equation, this problem together, in order to find how when the electrical diode will conduct, or when this diode will be treated as a short circuit. Of course, in the final exam or in the in-class test, whenever I give you such an example, I have to give you a hint and say that please treat your diode as an ideal diode, because later on we will have another model. So I have to distinguish, or I have to specify the model at which you will deal with your diode. So let's now go to this case. Here we have our circuit. This is the Vs, the source. We have the resistance, the 100 ohm. We have the diode. And then we have this 12 voltage DC supply. Now, what we are going to do is that we are going to solve or to analyze this circuit. The best way, of course, you know that the condition for this diode to operate is that to have the current in this direction. I mean to have this voltage, which is the anode voltage, to be greater than this voltage, which is the cathode voltage. Let's call the voltage drop across the diode VD. And now we can solve this as a KVL problem. So Vs, which is the supply voltage, equals to I times 100 ohm plus Vd plus the 12 voltage. This is your equation. Okay, so Vd equals to Vs minus 100 I minus 12. This is the output. You need Vd to be positive, so that the voltage here is greater than the voltage here. So whenever Vd is positive, then this means that your current, you are working in the right direction. I mean, the voltage on the anode is greater than the voltage of the cathode. Whenever Vd is negative or smaller than 0, then that means that you have this condition. Okay, accordingly, let's start to solve. So we have the equation Vd equals Vs minus 100I minus 12. we need this VD to be greater than 0 to satisfy that you are in the forward bias condition. So Vs minus 100I minus 12 should be greater than 0. Or Vs should be greater than 100I minus 12. Whenever these conditions happen, in this condition, you can deal with your voltage source as a short circuit. So when these conditions happen, the first starting point for this condition to happen is to have Vs equals to 100I minus 12. This condition, once this condition happens, then you can replace your circuit with a forward bias. Okay, so let's now plot the inputs. This is 24, and this is negative 24. Okay, and our equation is Vs should be greater than or equal 100I minus plus 12. As you can see, the first impression that this Vs should be positive, because I should be positive and 12 is positive. So this is a positive summation. That's totally mean that for any negative value for the current, for the voltage, that your diode will be treated as an open circuit. It will be a reverse bias, not a forward bias. Okay, and then what about the positive portion? I is the current. The minimum value of the current is 0. So the minimum acceptable value for the voltage will be 12 when you put I equals 0. So if the source voltage is smaller than 12, that means that 100% this condition will not be satisfied. If the voltage, if the output voltage is greater than 12, then your diode will start to conduct, and this equation will be satisfied. So your diode will conduct only in this region. From whenever your voltage is, this is the 12, I'm sorry. So whenever the input voltage is greater than 12, this region is the only region where your diode will be conducted as a short circuit. In this region, my dear students, let me return back to the circuit. In this region, my dear student, we will replace the diode with a short circuit. Otherwise, we will replace the diode with an open circuit. So this is the only given region at which your circuit will conduct. Otherwise, your circuit will not conduct. Okay, so this is a new example for a circuit based on an electrical diode, where we treat our electrical diode as a short circuit whenever it's a forward, and we treat it as an open circuit whenever it's reverse, or what we call it an ideal diode. In the next part, inshallah, my dear students, we are going to demonstrate other models, not only the ideal model. We have another 3 models where we can treat our diode. In the next part, we are going to demonstrate these models and say how we can model our diode as in circuit. Thank you very much for your concentration for part number 2, and see you in part number 3, inshallah.